Oil, the most sought-after commodity of the 20th century. Today, the world uses about 1,000 barrels a second, and the search for new reserves continues at a frantic pace. But oil hasn't always been so valuable or so difficult to find. For centuries, small pools and seepages have been exploited in many parts of the world. Increased demand led to the search for new reserves below seepages, and the first exploration wells, like water wells, were dug by hand. But not for long. In 1859, the American Edwin Drake struck oil in the world's first drilled oil well, and the industry as we know it had begun. Drilling ventures sprung up rapidly, as the technology of the time required little capital. For, once oil was discovered, everybody wanted a share. The fact that all these wells are tapping the same reservoir didn't seem to matter. Oil hunting, although exciting, was then a very dangerous occupation. This is the Murray Sudique Gusher, the largest recorded in the United States, which was out of control for months in the 1930s. The men who tried to cap it would never hear again, and all their attempts, including lowering 40-ton steel blocks onto the wellhead, failed. Worse still, crude oil can be very inflammable. Gushers were all too frequent in the early years of the industry, and although poor equipment was partly to blame, the main cause of most of these failures was ignorance. Most drillers hadn't a clue what they were drilling into, and the first they knew about oil in the ground is when it rushed up and covered them. The majority of wells at this time were drilled on the strength of a hunch, as the use of geologists in this matter was thought foolhardy before the turn of the century. But some did listen to geologists, and they drilled for one thing alone, the anticline. The anticlinal theory, put forward in 1844, envisaged this type of structure as the only possible mechanism for trapping oil. The geologists' only hope of pinpointing anticlinal structures depended on field mapping and geological intuition. But it was no easy task, for they range in size from the familiar folds of British beaches to the vast sweeps of the Zagros Mountains in Iran, and, unlike these, most have no surface expression at all. But the search continued, and as well as anticlinal traps, the other oil-bearing structures were found, some bounded by unconformities, some by faults, or even sedimentary barriers. Despite the growth of geological understanding, the only exploration methods available were field mapping and subsequent drilling until the advent of geophysics. Developed by scientists working on the salt domes of Germany, refraction seismic techniques were first used to search for oil in the 1920s. Seismic surveying allowed the search for the now well-known trap types to be continued below structures mappable at surface. And although oil couldn't be recognized directly from such surveys, broad structures certainly could. Equipment and processing has become a lot more sophisticated since the 30s, but it's still very time-consuming and expensive to survey large areas. So where should the geologist and the geophysicist search for oil? Let's remember a few basic facts. Oil is known to originate in sediments and is usually found in porous sedimentary rocks, so it's pointless searching areas of basaltic oceanic crust, volcanic or metamorphic regions. That leaves areas of continental crust covered in sediments, and here the search can be narrowed down further. Once formed, oil is often subjected to conditions which lead to its eventual destruction, and as a result, little oil is known in rocks older than 350 million years. What's left are the areas explored this century, and, after all the easily accessible onshore regions had been considered, only the shallow seas remained. In the rest of this programme, we'll examine how one such area was explored. This area is the North Sea, the area of greatest interest for British oil exploration. It's a relatively shallow sea, much of it less than 100 metres deep, and it's part of the continental shelf, truly a piece of Europe and not oceanic crust. Its geology is related to that of the surrounding countries, as it formed by the sinking of a large piece of continental crust. So what's the possibility of oil under the North Sea? Well, in the north, the rocks are old and metamorphosed, definitely not suitable for the preservation and accumulation of oil. But in the south, in most of England and in northern Europe, there are younger Upper Paleozoic, Mesozoic and Tertiary sediments, less than 350 billion years old. If the geology were continuous between England and the rest of Europe, then these sedimentary rocks should be present under the North Sea. The possible presence of sedimentary rocks is a step in the right direction. But before 1959, there was thought to be little possibility of hydrocarbon production from the North Sea. Oil had been found in many small fields in the Carboniferous, Cretaceous and Jurassic rocks of Germany and in the Carboniferous of Holland. And as you saw in an earlier programme, in the Carboniferous of Eastern England below this Permo-Triassic cover. And gas? Small amounts had been found in the Permian and Triassic rocks of Germany and Holland and in the Permian of Yorkshire. But none of these discoveries were large enough to encourage oilmen to look at the North Sea, where exploration and production of oil would be far more difficult than on land. But in 1959, this all changed. An enormous gas field was discovered below beetroot fields in northern Holland at Groningen in Permian sandstone beneath this tertiary cover. This turned out to be the second largest known gas field in the world. And as the gas in Yorkshire was of the same general age, this raised hopes that the area between the two, the North Sea, might also have large gas fields. All the interest was initially on the southern North Sea, where it was hoped that gas would be found under similar geological conditions to those at Groningen. And this was found to be the case. There were ample gas supplies in the southern North Sea for the near future. So in this area, the general geology was found to be continuous from Britain across to Europe. Now what about the north? We said earlier that it's flanked by mainly old and metamorphosed rocks, here in Scotland, through the Orkneys to Shetland and to Scandinavia. And up until the mid-60s, it was thought that similar rocks exist under here. Gravity surveys indicated that things might be different. Those surveys suggested that the centre of this area is a deep basin with up to 3 kilometres of tertiary sediment. It was this great thickness that attracted the oil companies, as large tertiary basins in other parts of the world contain many of the most productive oil fields. The surrounding countries divided the North Sea into blocks for licensing. British interests were high, and among others, BP took these two blocks here in the Forties Sea area. Why these? The bid for the blocks was based on reconnaissance seismic surveys, which looked for structures just as they had done on land in the Middle East. This long tube contains many small hydrophones spaced at regular intervals. They're all connected to recorders on board. The tube is towed along behind the ship. The reflected seismic waves which they detect are produced by an air gun. High-pressure air is released at regular intervals, producing seismic waves. These waves travel through the water and into the sea floor, where they are reflected back up to the hydrophones. The signal from the hydrophones is recorded on board ship, building up a seismic profile of the rocks beneath the sea. That all seems quite straightforward, But how exactly is the energy from an air gun turned into an interpretable record? Each hydrophone records seismic signals, and the reflection of a part of the input energy at the interface of two beds of different seismic character will cause a deflection on the output of each instrument. The greater the reflection coefficient, the greater the deflection. And the deeper the interface, then the longer the two-way time interval from firing to deflection. One record will indicate the time to a major bed boundary, but a series of records across an area can give us structure.
Well, that's always the theory, but geophysicists in the field often find their results much more difficult to interpret. In the Forties field, however, the theory and the practice came reasonably close. This is one of the first lines shot across the area back in 1965. And although the quality of the section is very poor by today's standards, it was possible then to recognize a continuous reflector and draw in this large, gentle anticline. A classic feature, and obviously one of great interest. We now had a potential trap, and it was considered well worthwhile to investigate further. Following the 1965 lines, one of which you've just seen, more surveys were shot across the area in 1966, 67, and in 1970. Obviously, for each of those lines, like the original, it's possible to produce an interpretation, and here, that same strong reflector is drawn on sheets representing the seismic sections shot up to 1970. The original two-dimensional representation of the anticline is now extended to produce this three-dimensional feature which plunges gently away to the southeast, with its shallowest part up here. That could have seemed very bad news, for any oil present would have probably migrated away up dip. However, the seismic showed a local downwarping here in the northwest, and that was sufficient to close the structure. If oil had been generated locally, and there was a reservoir present in the structure, and oil had migrated into it, then there was a very good chance that some of it would have been trapped as a result of this closure. Well, seismics at that stage couldn't show the presence of oil directly, and drilling was the only way to test whether oil was present in this structure. The first well on the 40 structure, called 2110-1, spudded into the seabed from the drilling rig Sequest in August 1970. The drill bit's downward passage allowed geology to be added to the bare geophysical framework for the first time, as cutting samples and core were recovered from the hole. However, all speculation on the likelihood of oil in the structure ceased in October when
So that belief in the seismic survey worked, and a very significant discovery was made. Britain has oil offshore. But how much? How big was the field? How fast would the oil flow, and for how long? Even if these questions could be answered, plenty of others remained concerning the best way to exploit the find. Production wells don't come cheaply, and their optimum siting requires more than a hunch. So the petroleum engineers require every last scrap of detail they can extract from the well and from those that follow, so that the nature of the reservoir is well known. From the well came chippings like these, and cores like these, which enable a lithological log to be produced. And here's that all-important boundary between the shale of the cap rock and the sandstone of the reservoir. A problem here, though, for the cores cost hundreds of pounds per metre to obtain, and under certain circumstances are so poor as to afford little detail. What other techniques can be used to build up a more complete record of the geology? It's downhole logging. This tube, or sonde, contains sensitive instruments which measure the physical properties of the rock layers that the well passes through. The sonde is lowered to the bottom of the well, and on its slow return to the surface records how the physical properties change with depth. One of the most useful techniques is a gamma log that records changes in background radiation from the surrounding rocks, which is a useful guide to the lithology. Here's the gamma log for this well, which shows the change in character across the reservoir cap boundary. The shales of the cap rock having a higher concentration of the gamma-producing elements than the mainly siliceous sandstones. The boundary shows up even better on this record from a sonic instrument. This measures the velocity of seismic waves passing through the rocks, with sandstones having a higher velocity than the shales. So by using all these methods, we can build up a very accurate but extremely narrow geological picture. How do we now relate this strip of geology to our broad structural picture fashioned from seismics? Well, here's a seismic trace from a reflection profile across the well, drawn on the same vertical scale as the other logs. These units are in milliseconds. We know that these reflectors result from changes in density and velocity across formation boundaries. And so it's possible by using these logs to correlate individual reflectors with geology, and so build up a full structural model.
Well, again, that's something which works fine in theory, but a fuller understanding of the reservoir is needed if the petroleum engineers are to exploit it efficiently. Our first well enables this type of model to be constructed, which shows the general geology. From the seabed at some 150 meters, there is a succession through the tertiary to the reservoir in the 50 to 60 million year old Paleocene below 2,000 meters. Nearly all of the upper tertiary is shale, providing an excellent seal to the sandstone reservoir rocks in our anticlinal trap. And the source? Well, that's probably down here in the shales of the Jurassic. So, we now have an oil field and can identify all four of the necessary components. But the detailed knowledge of the reservoir had yet to be collected. For this purpose, 4 more wells were drilled in the area, and geophysical techniques were used extensively for correlation between the different wells. In the first well, it's possible to compare the lithological log with the data from the cores and the geophysical well logs from the various downhole instruments. In other wells, geophysical well logs can be correlated with existing information and an appreciation of the geology built up with minimum recourse to expensive coring. Well information, as we mentioned earlier, can be tied in with seismics, and extensive work was done and is still continuing to cover the area with better quality seismic detail. The techniques both of shooting and processing had improved enormously since the first survey in 1965. And instead of the general features of the early lines, it's now possible to interpret lithology and map sedimentary units direct from the seismic sections, as on this current example. In fact, it was soon shown that the initial idea of a large uniform sheet sand reservoir was too simple, and the reservoir was seen to consist of a number of sand lenses in a variable sandy, shaly matrix. This discovery obviously modifies our estimate of oil in the reservoir, and this information, together with detailed seismic analysis of the reservoir shape, leads to the estimate of 1.8 billion barrels of recoverable oil. The need to map the top of the reservoir accurately can be appreciated with reserves of this size. A 1% error in recoverable reserves is equivalent to 360 million pounds at 1981 prices. And what does all this information give us? An understanding of the reservoir itself, such that production drilling can be planned most efficiently and the necessary platforms designed and constructed. In 1974, the first of 4 vast steel production platforms were installed over the field, and drilling started about a year later. From each platform, 27 deviated wells were drilled, some with horizontal displacement of over 2 kilometers, so that each platform drains the oil from some 15 square kilometers. Since production began, the field has averaged about 5.5 barrels per second, every second of every day. That's 500,000 barrels a day for the last 5.5 years. A very rewarding end to a search that began here.